This is our fifth lab. We're going to have one left lab which is about the dullness, and this is about the gas phase and gas reaction and gaseous, which is going to be the last lab after we cover chapter 10. So today we are going to highlight on the Lewis structure. So hopefully by the end of today you will have some more insight, and hopefully I expect you to be more confident about writing this structure, the molecular structure, starting from Lewis. You have to follow, and if you look at the handout that I gave you, it is actually giving you the Lewis structure rules and step by step again in the handout that I gave you. I want you to go over it, but this is going to help you, but it doesn't mean that it is going to be without you try yourself to do some exercise. So when you do the exercise, it will make you feel more confident about the material. So these are the objectives for this particular, hopefully students will be able to draw Lewis structure after we finish today, including molecular structure and polyatomic ion structure. Also, you're going to be able to construct the molecule models with using the ball and stick, and those are the box which are on your bench, every single one. If you need any more, we have extra over here, okay? So I wanted to put together those for you. Look, these are the standard.
Yeah.
All right, so what we have here, the valence shell, bonding electron pair, Vesper formula, bond angle. You see, these are the standard. These are generic formula. Now, every single one of those are without non-bonded lone pair. It's all are bonded lone pair. And then we look at the bond angles for each one of those formulas. And also we are going to have the geometry, the geometric shape, which is when you are going to have only two surrounding the central atom, it is going to be AX2, the bond is going to be 180, this is going to be linear, and then we are going to have the shape of it, it is linear, and it is actually giving you that here. So the bond is going to, give me an example. Can you give me an example?
Of linear?
Of the linear, AX2.
CO2.
Oh,
AX2, what is that?
CO2.
CO2 is linear, that's right. Okay.
H2O.
And we have, for instance, BCl, also BCl2, right?
Actually,
Or BeCl2, earlier. Now, what about the triangle, like in a trigonal planar? When you have the central, this is A stands for the central, and then the X are the surrounding atom. So if it is surrounded by 3, give me an example.
H3O.
Huh?
H3O.
H3O?
I don't know.
No.
No?
No, we are not talking about the molecule that has non-bonded lone pair. Remember, everything is bonded. And so we have boron,
BCl3.
trichloride, something like that, or
AlCl3.
also
AlCl3.
Al, what?
Cl3.
Cl3?
Yeah.
Yeah, it's under the same, but remember, Al is metal.
Yeah.
And we want to look for either metalloid or non-metal, because we have a covalent bond, right? Not ionic bond. And also when we are going to have a tetrahedral, what is it going to be? Give me an example about
CH4.
the CH4,
CCl4.
CCl4, and etc. When you have 5, it's trigonal bipyramid, and this is the shape. We have 5 electron or 5 atoms surrounding the central atom. Any idea? Give me an example.
PCl5?
PCl5.
MCl. No, it's not.
Now, when we are going to have 6 surrounding the central atom, octahedral, like SF6. So these are examples, and also they are giving you more examples about these kind of. Now these, all of them are without any non-bonded lone pair, but the reason why I listed them here for you, because you're going to take it as a guideline for you, okay? In other words, we found out, like, if we are going to have PCl3 instead of PCl5, what is it gonna happen? So the phosphorus is going to have only 3 to be able to, only 3 atoms surrounding the central atom. So, and then the other is gonna be the non-bonded lone pair. If I want to consider this as the 4th arm, then it is going to look like a tetrahedral, okay? Because this is a standard, all right? Standard, whether this is the Vesper formula. But if we are going to remove one of those, replace it with non-bonded lone pair, the molecular geometry is going to be different. But the electron geometry, it is going to be the same. And we know that, right? Hopefully everybody by now know the differences between the two. Between molecular geometry versus electron geometry, right? So when I'm going to replace one of those with another non-bonded lone pair, which is, we call it the electron group or electron domain, then the electron geometry is going to stay the same as what we have in the standard, okay? So this is something that we want to look into and be careful with, okay? So we are going to go over a couple of these examples, all right? And then we are going to refer to the standard. So when you're going to look into your handout, everybody, they are giving you example. I really like this handout because it is actually explaining to you Lewis structure. And if you have a polyatomic ion, you'll have minus, meaning we're going to add to the total number of electrons, right? Adding, if it is a negative, in other words, if it is a anion, you add electron to the total number of electron of the molecule. If it is positive, then you are going to add, to subtract, okay? So that's when you have polyatomic ion. Also, they referred to the actual, like, the history of the molecular geometry. It says, like, they are going to use the scanning tunneling, but most of the time, as you hear me talking to you, it's X-ray. Under the X-ray, the scientists were able to capture one molecule at a time under the gas phase, not in the, like, liquid or solid phase. So those are the, like, how it started. 3D was started when they were, like, starting the new technology, and this is the X-ray, which is one of the electromagnetic radiation. And then he was mentioning something about the Lewis structure and formal chart. In the formal chart, we try to make sure that every single atom in the whole entire molecule will have the least, like, formal charge. In other words, 0 plus minus 1. We try to make it, like, this way. Now, what is the formula of the formal charge? You have to memorize it. It's equal to the valence
minus
electron of the atom. The atom valence electron only. Subtracted, and then you open bracket. Equal here, the number you're going to count, the number of the non-bonded electrons, right? Or we call it ion pair electrons, right? Plus half of the bonded electrons. And this is going to be, like, bonded pair of the electrons, and that's how you're going to calculate the number of formal charge. We did a couple of these examples. And then if you go further into 9, you're going to see sorry. Thank you. You're gonna see there are, another terminology. Can you see what it is? Tell me what it is. So you see here, over there, we can see the formula for the formal charge. Okay, what did you see from that table? Number 9. There is a table on the bottom. Group of electron ground central atom. They are giving you the surrounding atom. If it is 2, 3, 4, 5, 6, and this is exactly what we had here. And then they're giving you the angular, in other words, the angle, bond angle. And what else is there? Hybridization. So I'm going to give you some insight to that. This is a heads up for chapter 9. So just give me a couple minutes. I'm going to refer to each one of those, if we have 2 surrounding the central atom, if we have 3 atoms surrounding the central, if we have 4, if we have 5, and we have 6, okay? So I'm going to give you, because if you don't understand what is this, what is that? What is SP? What is SP3? What is SP4? 2, SP3D, or SP3D2. So these are called hybridization, okay? So I'm going to go over these with you. And then please let me know. I'm going to erase that. Let me know if you did not understand what I'm doing so I can also, highlight on it again, okay? So, all right, so I'm going to take each one of those, and then I'm going to do the hybridization for it, okay? So, when we are going to have 2, it could be CO2, it could be beryllium. So I'm going to take the beryllium. Beryllium, what is the number? In other words, the atomic number is 4, right? So the electron configuration is SS, 1, 2, 2, and 2, that's 4, all right?
Yeah.
So we are looking at this, only the outermost shell. I know that's also, we do have 2p, right? You got it? You agree with me? We also have SSP, right? So in the n equal 2, I have S and I have P on the same level of the energy, okay? Now, I want to ask you a question. How on earth beryllium is going to be able to accommodate 2 atoms from Cl? If it has 2 paired electrons. How is it going to accommodate those 2?
The P block. From the P block.
The P? So what is going to happen?
Um,
In other words, let me make it easier for you. In order for any atom to couple with another atom, it has to have a single electron, right? In the outermost shell. If it is double, it doesn't. You agree with that?
yes.
In other words, I should have 2. If this is empty, okay, I'll bring another one and it is going to be paired. But what are we going to do if it is going to have no single electron? Everything is doubled. What happens, all right, the atom itself, beryllium, will rearrange its own ground state electron configuration. One of the electrons, Ali, one of the electrons are going to move into the P, which is under the same, it's similar in the energy level, right? And it is going to be, we call it promoted. So here, electron promotion will happen. This is step 1, okay? So we know when we talk about the geometry and everything, it is about the valence shell electron pair, valence shell. So that means we are after those, the outermost shell, which is 2 level, all right? Now, after promotion, what are we gonna end up having? And I'm after those two. So what we are going to have one here and one here. Okay? Is that clear? Okay. So when we are going to have this, then the beryllium will be able to accommodate 2Cl. All right? Now, this is not going to stay like that. It is going to be connected. All right? In other words, overlap. Overlapping of the orbitals. Okay, so we're going to have overlapping orbitals. They are going to make one type of orbitals. It's no longer just S, it's no longer just B. Every single one of those orbitals will be called sp, 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 and sp. We have two missing. In other words, space doesn't have any, but those two are going to be accommodated. And that's why beryllium will be able to accommodate those 2Cls. Okay? This applies to C in the middle with oxygen. This carbon, all right, has sp, but the oxygen is sp2, hybridization, okay? And the S is also going to have 4 in the outermost shell, okay? And we're gonna have electrons coming, one from the S and the other one from the P. So we're gonna have sp, 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 and sp. And then we're going to be able to accommodate those two oxygens for the central carbon. So also we're going to have C triple bond C. That's also sp, hybridization. Do you remember, how are we going to be able to adhere to this kind of rearrangement? What do we mean by hybrid car? Hybrid car. What's the difference between hybrid carb and regular carb? What is the difference? It has what? How is it going to work, the engine?
It's powered by both electric.
Come on, guys. This is general knowledge. Everybody should know that. Why are you looking at each other's face? You don't know what hybrid car is? What's the hybrid car?
It's powered by both an electrical.
Electric and fuel.
Yeah.
So it has two, right? More than one system is going to ignite or start the engine. The same applies here. Hybridization. Orbitals are going to be hybridized. In other words, overlap, and it is going to make one type of a orbital that we call it hybrid orbital. This hybrid orbital is made from two types of orbital, from S shape and from the P shape. Okay? That's why we call it hybridization. Got it? Now? No? Somehow? Maybe? All right. So this is what we mean by hybridization, okay? So things like this, when we're going to have those steps. So first you have to do, and we're going to have more into that in the following chapters. But number one, by the way, and we should know that VSEPR, Lewis structure is always focused on, and hybridization always going to focus on the central atom only. Central atom. And then from the central atom, we are going to look into the rest of the surrounding. But the most important focus on Lewis structure is the central atom. Remember when we talked about structure, I said you have to be careful to choose the central atom. Then you choose the surrounding. Central atom shouldn't be hydrogen. Central atom shouldn't be fluorine, right? So these are the very important factors that we have to follow when we are going to draw the structure and decide or predict the shape of the structure, molecular structure, okay? So this is SP. So we know when I'm gonna erase everything and then replace it with the type of the hybridization. So the first one, I have the central atom surrounded by two atoms. This is an SP type of hybridization. What if we are going to have three surrounding the central atom? Then it is going to be, and I'm going to show you that, it is called, or we're going to call it, in other words, the shape of this molecule, in order for the beryllium to be able to accommodate two, it has to have two singles. If you have two electrons pair, then how is it going to be able to combine with another element? It can't. Two in the outermost shell, I have only paired electron. It is not going to be willing to accommodate or pair with any other atom, unless if it is single. Now, when it comes to the sp2, and I'm taking boron trichloride, okay? So with the boron, I know boron is 5, number 5, right? So electron configuration, and I do that, all of it, just to be in the safe side, so you know where are these coming from. So I have SSP, 1, 2, 2, 2, 2, and 1, right? In the outermost shell, I have 3. But one of the S, the 2S, that's a 2S, it has 2 electrons, and the 3 of the P has only 1. So the same thing is going to happen. Number 1 is a promotion. Number 2 is overlapping. Overlapping, and it is going to come across each other, and they are going to hybridize. So this is the promotion, is one of them, one of those from the S will be promoted to P orbital. One of the S electron is going to be promoted to a P orbital. And we know P orbitals, although they are almost the same, but it is a little bit higher in the energy than S, right? So that's why we call it promotion. When we are having promotion now, we have 3 single, right? 3 single. Now, this is not enough. Number 2, then we are going to overlap all of those 3 together. So those 3 are going to be overlapped. I'm going to draw it in a different color so we see the differences. So these 3 will come together, overlap together to make one type of hybrid orbitals, 3 of them, and this stays empty, by itself. So now, one of this particular box is from 2s, right? Those 2 from 2px and 2py. Do you agree with me? Everybody? Are we following so far? Now, when I am going to overlap those into this, then it's no longer 2s, no longer 2p. We have sp2 now. Where is the 2 coming from?
The 2p of
From the 2 p's that we're going to use, exactly. So we pulled 1 orbital from s, 2 orbital from p. That's why we call the hybrid orbital sp2, sp2, and sp2. So we ended up having three hybrid new orbitals called sp2 orbitals. Each one will have 1 electron. Therefore, boron will be able to accommodate 3 chlorine, bromine, whatever, okay? That's how it is going to be able to accommodate. If it is kept like this, it's not going to be able to accommodate 3. It is going to be BCl, just that one. And by the way, somebody will ask, how would we know this is what happens? Can you tell me how? Julia? because we cannot find BCl in the nature. Got it? We can't find it, but we do. We're able to synthesize, extract it, purify, and isolate PCl3. Okay, boron trichloride.
Alright.
Is that clear, everybody? So the hypotheses came after they were able to find those chemicals. Then there must be something, they were puzzled. How did that happen? So they came with this postulation. You have a question? All right. So that's the only way that it explains what's happening in the atom. Otherwise, these molecules does not exist, right, in the nature if it's not going to happen this way. You got it, everybody? Are you clear, everybody? Do you have a question about what we are doing here? What do we mean by hybridization? This is a postulation that came across when they were able to discover or create those chemicals. So they have to come with an explanation. What happened? There must be something happened with the outermost shell orbitals that actually rearrange itself to accommodate the incoming atom. Otherwise, it's not going to work, right? It's not going to happen. It is not going to exist in the nature. All right? So this is for sp2. And then we go into sp3 when we are going to have four single electrons surrounding. So I'll take the CCl4 or CH4. It is going to be sp3, right? Let's take carbon. Carbon 6 electron total, so it is ssp. 1, 2, 2, 2, 2, and 2. In the outermost shell, I have total of 4. But look at it. I also have 1 paired and then 2 only single. If carbon keeps its own electron configuration like this, that means we're only going to find CH2 in the nature. But we never did. Got it? It has only 2 single. Each one is going to take H. And that's it. So how come we are having methane in the nature? How did that happen? So somebody has to answer this question, right? You ask yourself this question. How on earth we were able that carbon will accommodate 4 hydrogen instead of only 2? So this is what happens, exactly the same as what happened with the previous. One of those electron will be promoted and it's going to jump into the p orbital, okay? So number 1 is promotion, number 2 is overlapping. So when we're going to have the promotion, we're going to have 4 single orbital with 1 electron, okay? And this is from S, this is from P, like a PX, PY, and PZ, and all of them are 2, right, in the second. But now, when they're going to overlap, all right, it is going to come together, and we are going to have, what are we going to call this hybrid orbital? 1s and 3p. What do we call it? sp3. So it is sp3. We're going to have four orbital, new orbital, and we call it new hybrid orbital, that it is made from 1s and 3p. And sp3 and sp3. Okay? So that's the new one. And now, if I have 4 single, I can bind it with Cl, with fluorine, iodine, or even hydrogen. Okay? So that's why we were able to see and have methane, or carbon tetrachloride, or carbon dichloromethane, or so on and so forth. Okay? Do you have a question about what we had so far? All right, we can continue further. and we go to PCl5 and SF6. So I'm gonna give you the hybridization of this guy with five atoms surrounding the central atom, and then we are going to go into sulfur, which is surrounded by 6 atoms. So when I have PCl5, phosphorus, what is phosphorus? 15, right? So I have the electron configuration SSP, SP. It is in the third period, the last is gonna be in 3. Those are 2 and this is 1. 2, 2, 6, that's 10, and 2 and 3, it is 5 only in the outermost shell. But look at the way that they were distributed or organized. In the regular, when phosphorus by itself, before combining with another element, we have 3 s2 electrons, and I have 3 single in the phosphorus. Is 3px, 3py, 3pz. All right, but the molecule phosphorus is surrounded by 5. That means it needs 5 single. We cannot accommodate 1 double or like in a pair. So how many do we need total? We should have total 5 single electrons. Now we know in the third level, what do we have? We also have a D type of subshell, right?
Yeah.
So we have 3D that has how many orbitals? 5 orbitals, okay? Within the same level, remember N1, N2, N3, N4. So in N3, I have 3S, 3P, and 3D. One of those will be promoted into 3D. One of those pair of electrons. And now we are going to have 5 single. And we have, listen to this. 1 is coming from 3S, right? I have 3 from P, 3P, PX, PY, and PZ, right? And then I have 1 coming from the D type of subshell. So over here, I have the other one, like 3D. So we're going to have how many single? Total 5, right? And that's how phosphorus can accommodate 5 atoms surrounding the central atom, based on this theory. You got it? So this is a promotion, that's number 2. Number 3 is the overlapping. Those are the 5 going to overlap, making a new hybrid orbital. What do we call the hybrid, the new one?
DSP3.
1, 2, 3, 4, 5. Should be 5 of them. Huh? What, sorry, what is that?
DSP3.
SP3D. You cannot start from D. SP3. SP3D. SP3D and SP3D. And the last one, SP3D. So we have 3 from P orbital, 1 from S, and 1 from D. That's why the hybridization for PCl5, SP3D, that's where, what's the hybridization or orbital is coming from, okay? So, according to these numbers, that means how much orbital, how much boxes we do have. SP3 meaning we have 1 box from 1 orbital from S, 3 from P. Over here, 1 from S, 2 from P. 1 S from 1 from P. Here, I have 1 from S, 3 from P, and 1 from D. What's going to happen when we are going to have 6 surrounding the central atom? Then we need another one from D. And that's where we are going to have SP3D2. Okay? Try to figure that out with S, with sulfur. Use it. Let's see how we're going to be able to make it. Try it. You have sulfur surrounded by 6 fluorine, sorry. So first, what did I do? You have to take the central atom, do the electron configuration for it, and look for the outermost shell electron orbitals, and then work with it. Try to accommodate 6 fluorine. So then sulfur should have 6 single in the outermost shell instead of, like, you know. So first, number 1, what we need to do is to make sure how many electrons we have in the outermost shell for sulfur. Remember, sulfur was able to accommodate 6 electrons surrounding, 6 atoms surrounding sulfur. What is sulfur number, atomic number, Maria? 16. So 16, you do the, give me the electron configuration of sulfur.
3s2.
SSP, SP, right? 1, 2, 3, and 2 and 3, 2, 2, 6. That's 10, and then I have 2 here and 4 here. All right, so how many we have in the outermost shell? Those 6, okay? 6 electrons in the outermost shell. So, again, we have 1 coming from the 3s, it has 2 electrons, and the other one, it has 4. 1, 2, and then 1, 2, 3, 4. But that means we should be having SF2 only. Oh, we see SF3. Oh, sorry, 6. So that means we need to have another 2 single. Okay, 2 single. So we are going to jump into the D, 3D, 3P here. Okay? And 3D has 5. 1, 2, 3, 4, 5. 1 coming from this, and the other one is promoting there. So we're going to have 6 single electron in the outermost shell. Okay, by number 1 doing the promotion, number 2 we are going to do the hybridization. So try to do that. I answered the question for you. So that's covered most, if not all, of what we have to know, like, you know, about the hybridization that we are going to accommodate or, like, you know, address in the following chapter. But since it is mentioned here, we need to learn about it. We need to know, what do we mean by that? What do we mean by hybridization? So this is going to conclude, like, you know, at least how this particular phenomena, it is going to be able to make it, like, you know, reality. So when they are going to be promoted first, so what we have, we're going to end up having 1, 3 single here, and we are going to have another 2 single from D. And then all of those, 6 of them, are going to overlap, coming together, overlapping, making a one type of new hybrid orbital that it's called, what are we going to call that? 1, 2, 3, 4, 5, 6. What are we going to call it? What's the name of the hybrid orbital, the new one?
SP.
1 from S, 3 from P, 2 from D.
SP3.
SP3D2. That's how it is going to be called. Every single one, SP3D2. And it has 1 electron and willing to accommodate another 1. Whatever you want. Okay, so now sulfur can accommodate 6. Fluorine, chlorine, bromine, whatever you want. Okay? Is that clear? Yes.
So can one atom kind of form different hybridizations, like carbon?
Yeah.
You see how carbon has CH3?
Yeah, CH3, but then you have 1. This is CH3, cannot be found without CH3. What does that mean? CH3,
Oh,
radical.
radical, yeah.
You cannot find this now here. I mean, I cannot
CH3
make it. You cannot see it in the regular atmosphere. It is found in the upper altitude and atmosphere. Why? And why is that?
It's not.
Anybody knows why we are able to find CH3 radical in the upper altitude? CH4 is going to go into the ultraviolet and heat of the sun, that it is going to allow it to kick out one of these hydrogens, okay? So now we're going to have this hydrogen. But this guy is not going to go by itself. Anyway, hydrogen radical is highly unlikely to be found. If you have this one here with Cl2, then yes, you will be able, or any of those gas in the upper altitude. And this is basically what happened with the ozone layer, that we ended up having a broken, like, even with the O3. The O3 is made with the 3 oxygen. One of the oxygen will be kicked out, making oxygen 2 plus O. That one is going to react with Cl, another radical, and then the reaction is going to be continued, never stop. It's too hard to stop. The radical is too hard to stop. Once it started, it will go all the way into, in other words, this is going to make C3Cl plus another,
HCl.
and then it's going to go CH2Cl2, and it goes into CCl4. But then, as long as you have methane in the upper altitude, and as long we have chloride or any of these polluted gas, the reaction will continue as far as we know, because ultraviolet electromagnetic radiation is there available. We cannot control it. And the heat of the sun is there. So all the conditions required is available. And therefore, people from, presidents from all over the world, they met, right, in Glasgow, and then, they wanted to make a control on what's going on in the pollution and the, ultimately the climate change. So that's only the time then when you find CH3. Otherwise, you cannot have it available. Okay? So I think we are okay now. You can continue. I want you to work as a group of 2 or 3, whatever your group, and then follow the whole entire assignment that you have here. At the end of the day, you need to submit your lab report with answering the result and discussion, experiment number 6, page number 71, Lewis structure and molecular model, and then carry on all the way to page 73 and 74, okay? So that's what we are doing together. I'm going to come across each group, and then we can work together. You can ask me if you have any question, we can go over it. But as of now, do you have any question for me? Is everybody okay? You know what we are doing here. As I mentioned, this is a dry lab. We are highlighting on the topics that we covered in chapter 8, and hopefully by the end of today, you will be able to visualize. So using these boxes, you will be able to visualize the 3D of Lewis structure, and molecular modeling will help you. So whenever you see any of these, try to put them together. Now, I want to tell you something. The green is the chlorine. Okay, this is the chloride. Sometimes you see it here in the back, they are telling you, like the back of the lid, giving you the list of them. Now, if you are going to have the purple, this is ammonia. Sometime ammonia, it is the blue one, you can always use it. What is this molecule? Water. It's 1 oxygen in the middle, and it is surrounded by 2 hydrogen. And look at it. How the shape of it? The shape of this molecule? Bent. We are not considering the other 2 non-bonded lone pair, right? So, because this is a molecular geometry, not electron pair geometry. So that's the difference, okay? And then we have the black, which is the carbon atom. And if we have something phosphorus, it should have 5 These, if you have these, it's like, you know, the ear, the elephant ear we call it. This is the non-bonded lone pair. All right, if you have them. So this is how we are going to use it. We do have a couple extra here if you need it.